Right. So, in our course selected topics in decision modeling, today we are in our lecture number 19 and we are in the middle of the travelling salesman problem discussions. So, travelling salesman problem, as you have seen earlier, that the formulation of the travelling salesman problem as an integer linear programming becomes like this. So, usually what happens in a travelling salesman problem, the salesman travels from a given city to a number of cities and goes to all the end cities exactly once and comes back to the city of origin. So, because of the nature of the problem, the formulation becomes minimize z equal to sum over I, sum over j, C I j, x I j, where I is the starting city and j is the ending city, and x I j will have only 0 or 1 value, and subject to the sum over x I j equal to 1, sum over I as well as sum over j. That means, there should be only a single starting city and only one city where it will arrive, the salesman will arrive. But that much formulation, as we already have seen, is the same as that of an assignment problem, although the two problems are very different. The additional constraints that you also find in a travelling salesman problem is that the subtours must be blocked, right. We should have a complete tour and we should not have any subtours. So, we have seen before that how to block those subtours, how to write the constraints for the subtour blocking. We are not going to discuss that anymore. Only thing to note here, the assignment problem solutions gives us a lower bound for the TS problem. So, we have solved a problem in our last class, if you recall, where we had the assignment problem solution and the same assignment problem solution comes out as the optimum solution for the travelling salesman problem. So, assignment solution gives a bound, but this bound, if it becomes optimal for the travelling salesman also, then there is no need to solve any further, or in other words, the branch and bound is not really required. But what happens if it is not? So, as you can see here, the steps once again, they ignore the subtour elimination and the resulting problem is an assignment problem. Solve the assignment problem by Hungarian method, and if the optimal solution provides a complete tour, that is no subtour, then it is also the travelling salesman problem optimal solution. So, we stop. So, in our previous example, we have solved the assignment problem and we stopped. But what happens if the assignment optimal solution is not giving a complete tour? If we have a subtour, then we should go further. What do? We take out of the difference, there will be some subtours instead of a complete tour, take the smallest subtour. Let us say the subtour has got 2 legs. So, we branch the problem, the main problem, to 2 branches, and if the smallest subtour has got, let us say 3 branches, then we branch into 3 such branches. Then assume there are k sub problems or branches, then solve the sub problems P 1, P 2, P k and proceed with the BNB algorithm. What is that? Solve one of the sub problems. If the solution of the resulting assignment problem provides a complete tour, it provides an upper bound, otherwise go to step 3. Really what it means? It means that if the sub problem really becomes the minimum tour length. How to know that minimum tour? Basically check all the end nodes, that is our step 6, that is it is the lowest of all the bounds of the end nodes, but if it is not, then we have to fathom all the unexplored sub problems, right. So, those are the steps. Now, let us look at a problem and see how these steps are executed. Supposing we have a 5 city traveling salesman problem as given here, and we need to solve it. So, first of all we need to find the lower bound by solving the TSP by the assignment problem. So, let us see how to do that. So, solving the assignment problem first. So, as you can see here, the particular problem that we have taken for Hungarian method, what we have to do? We have to do row wise and column wise reductions, and after doing the row wise and column wise reductions, the zeros that we shall get, we should try to assign in those values. So, see, first of all, you have this matrix here. So, those which are identified by red, those are our column wise minimum, the row wise minimum values. So, in the first row the minimum is 3. So, we deduct 3 from all the elements. Look here, 10 becomes 7, 3 becomes 0, 6 becomes 3 and 9 becomes 6. Is it all right? So, we have the row wise reduction of the minimum amount. Similarly, we do for all the rows. So, after doing all the rows, if you see, we have got 1, 2, 3, 4, 5 zeros. Is it all right? Now, we have to do column wise reduction. So, column wise you see 0 is minimum, 0, 0, 2 minimum here and 0. So, obviously, if it is 0 minimum, there is nothing to deduct, but in this case because the minimum is 2, we have deducted 2 and we got 3 becomes 1, 2 becomes 0, 3 becomes 1, m remains and 3 becomes 1. Why m remains? Because m is such a very large number, essentially that a to a, b to b, c to c we cannot assign. So, they are replaced by very high numbers. So, see, these are our zeros. Look at the zeros. So, we have all these zeros, right. So, all these zeros we have to now make assignment. If you look carefully, then you see that some zeros are in pairs, right. Because those zeros are in pairs, if you assign in one, the other one cannot be used. So, can we make all the 5 assignments? Let us start with some unique zeros. So, this one is an unique 0. Suppose we make some assignment here, right. So, let us do once again. Supposing we make some assignment here in this unique 0, and then this is also another unique 0. So, we make some assignment here. So, we made 2 assignments, but then out of these the remaining ones, suppose moment we have this 0 is gone, moment we have this 0, then this 0 is gone. So, you see we have been able to make 4 assignments with the available zeros, right. So, we cannot make all the 5 assignments. So, what we have to do now? We have to make more zeros, right. So, you see, although we are really solving traveling salesman problem, but the assignment problem itself has given us some difficulty which we did not face in our previous lecture. That time just by row wise and column wise reduction we could make all the assignments. So, when we have such kind of difficulties, that means we are unable to make all the assignments simply by row wise and column wise reduction. What we really need to do is we have to create more zeros. How to create more zeros? By a clever method, by covering all the zeros and then do some matrix manipulation, so that more zeros are created and existing zeros are more or less not changed. So, what is that method? Let us see that. So, this method will be like this. So, you see we could make only these 4 assignments as I have shown you earlier, and these 2 zeros are not possible, because we have some other 0 where we have made assignments, then we should do. So, what exactly we should do now? Here is a method, that method is given here, and using the method really does what? It actually tries to cover suppose we have been able to make 4 assignments and we have 2 other zeros. This method essentially covers all the zeros by same number of lines that is equal to the number of assignments. So, how many assignments we have made? 4. So, we are allowed to have 4 lines to really cover all those zeros, right. It should be very clear to you that although there is a proof, but I am not going into the proof and all, that we should not have more number of lines to cover all the zeros, because if we have more number of zeros, then the problem's optimality will be altered. It is all right. So, we should be careful that we should not have more number of lines to cover all the zeros than the number of assignments that we have made at a given point of time. So, what we do? See, the method is that if you are very intuitive, you can also draw those lines just like that, but this method if you follow, it will guarantee you that you can cover all the zeros by exactly same number of lines. Those are have actually the number of assignments. So, the first method, make rows that do not have assignments, right. So, which is that row that do not have assignments? You are clear that this is the row, right, it does not have assignment, all other rows have some assignment. So, if we choose this particular row, that is where a tick is given, then you choose marked columns that have zeros in the marked rows. So, this row is marked. So, where are some zeros where in the marked row, obviously this is the column. So, this column is chosen, right. So, these 2 are chosen. The third is mark rows that have assignments in marked columns. So, in this is a marked column. So, in this marked column there is an assignment, that is this one. So, we mark that row also, right. So, we have marked 2 rows and 1 column, and then the process should be repeated, right. The repeat last 2 steps still possible. That means, now we have marked 1 more row. Is there any other 0? If there would have been 0, we could have marked that column also, but fortunately for us there is no such column. So, we stop here. Now, what we do? Draw lines through unmarked rows and marked columns. So, these are unmarked rows, we draw lines, and this is the marked column. So, we draw lines, right. So, this is how you see the 4 lines we have got, and those 4 lines exactly cover all the 6 zeros that we have got so far, right. And also the number of lines has become equal to the number of assignments. Now, what? Now, you find the minimum uncovered element, which is, see, now certain numbers are covered, certain numbers were doubly covered, the intersecting, and try to see what is that number which is the minimum and uncovered. So, you see these one is and these one, they are the minimum uncovered element. So, call that P and P equal to 1. Is it all right? So, next what we have to do? We have to subtract P from all other uncovered elements, that means these ones will be zeros, and add P to all the intersecting elements. Is it all right? Now, why is that? We shall understand this. Let us go to the next slide. So, you see, if you see the next slide, then again those things are written. See, essentially what you are basically doing, you are deducting P from all the rows. So, you see you are doing this minus P minus P minus P. Is it all right? So, you are deducting P from all the elements. Is it all right? So, you are deducting P from all the elements, that is the first job, and then you see those covered lines. So, wherever you have covered lines you are adding P. So, you see this is the matrix manipulation that we are doing. The manipulation is that we are deducting P from all the rows and columns and we are adding P to those rows and columns where we have got lines. Is it okay? So, essentially what will happen, those items which are uncovered, they will be deducted by P. Those items which are covered, their minus and plus will cancel. So, there will be no change, but those intersecting elements will go up by P. I hope you understand that the uncovered elements P will be subtracted, the covered elements minus and plus will cancel. So, nothing will happen, but intersecting element P will be added, right. In this case the value of P equal to 1. So, what is that? That is the resulting matrix. They look here, 7 has become 8, 5 has become 6, and these are the two intersecting element. M anyway does not change because M plus 1 is M only. But these rows, other items have not changed, but there 6 has become 5, 2 has become 1 and 3 has become 2, and these are 0, 0, 3 and 0 and M, right. So, with that now we can see that we have been able to make all the 5 assignments. A note about making assignments, please see that while you make these assignments, try to make assignments in unique zeros. So, this is an unique 0, assign. This is an unique 0 this way, so assign, right. So, this then once you have, then this is another unique 0, so assign. So, this 0 will be cut off. So, moment this 0 is cut off, obviously you can make another assignment here, right. So, we have been able to make all the 5 assignments. The assignment problem is solved and the unique assignments obtained are A to C, B to E, C to A, D to B, E to D. So, that is the assignment solution, and if you look at here, the solutions are indicated in the original problem, and if you add them 4 plus 3 plus 2 plus 1 plus 5, it is going to be 15, and that 15 is our TC star, right, and this is our solution A to C, B to E, C to A, D to B, E to D. But what it speaks about the travelling salesman problem solution. If you combine, then A to C, just look here, A to C and C to A together combines to A to C to A. Just you are clear, it is, if you think, you will find that this is a subtour, right. A subtour has been obtained. There is another subtour, that is B to E, E to D and D to B. So, B to E, E to D and D to B. Can you see that we have got another subtour here, that B to E to D to B. Is it all right? So, we have in this travelling salesman problem basically two subtours, A to C to A and B to E to D to B. So, we do not have a complete tour. So, the solution is not feasible. So, we need to branch further. Question is how? So, how do you branch? Please remember the steps that I have told you earlier. Choose the one that is having the least number of the legs or branches. So, in this case A to C, C to A, that is the smallest subtour, this is a bigger one. So, how do you branch? A to C, block A to C and block C to A, right. Block A to C and block C to A, those will be the two branches. So, let us see those branches now. So, if we do, look here, this is AC bar, that means put AC equal to M and CA bar, put CA equal to M. So, two sub problems. So, this is sub problems P1, AC has been put to M, CAC M. So, that means the cost for A to C becomes infinite and here C to A becomes M. So, these are going to be our two sub problems. I hope it is clear to you now that how do we go about the two sub problems, is it all right. So, once we have those two sub problems, now solving P1. So, what has happened in P1, if you look at once again, we have put AC bar, that means A to C we have blocked. So, A to C has been blocked here, just look carefully, A to C has become M. Now, again we solve, so I am not going deep into it, that means row wise again we find out the minimums and we deduct them row wise. So, we do not have to start from beginning, we can start from the matrix that we already had. So, if we now because because a 0 has become M, so we put like this and we see a solution has been obtained once again. What is that solution? A to D, D to C, D to C, C to A. So, again a subtour is there, A to D, C to A and B to E to B. So, B to E and E to B. So, these are the two subtours. So, again we have an infeasible solution and the bound value is 17. Where from we got? Look at the original matrix, the solution is put there and if you add 6 to 2, 8, 12, 15 and 17. So, that is the solution of sub problem P1. What is the solution for the sub problem P2? Right. So, sub problem P2, here we have put C to A to M, right, it is the other one, C to A has been put to M, and after row wise and column wise reduction, we find the solution as A to C, C to D, D to B, B to E and E to A. So, A to C, C to D, D to B, B to E and E to A. So, you are right that what you are thinking, I am also saying the same thing, that we have now got a feasible solution for the travelling salesman problem, right. And what is the bound value? The bound value is 3 plus 2 5 plus 7 12 plus 1 13 plus 3 16. So, the current bound value is 16, is all right. So, for sub problem P2. So, if we now put both of these into one place, then we see that the P0 had value of 15, P1 value of 17, but infeasible, and P2 is feasible and the value is 16. So, what we have to do, just carefully look at all the branches. What are the n nodes? These two are the n nodes. Now, out of the n nodes, which one is the minimum bound? So, look here, it is a minimization problem. So, which one is the minimum out of all the bounds, which is the most minimum? 16, that is the minimum. So, out of them, is it feasible? Yes. So, this is optimal, right. So, find out the lowest of all the bounds, and if it is feasible, obviously that is also optimal, right. So, we do not have to branch any further, and that is going to be our optimal travelling salesman solution, and that solution is A to C to B to D, E to A, and the total T C star equal to 16, right. So, that is how the branch and bound algorithm can be used. Now, this is not the only branch and bound algorithms. There are other methods available for branch and bound. In fact, several branch and bound algorithms are available. One such branch and bound was the oldest one, where we have a penalty based method. There are other methods, there are also branch and cut methods and so on so forth. There are a lot of research that is going on, and how to solve the travelling salesman problem in a very efficient and effective manner by using branch and bound algorithm. Is it all right? But before leaving this topic, let us look at another problem and quickly understand how this branch and bound method really works one more time, right. So, let us take another problem. Suppose we take a 6 city TSP problem as given here, and again we need to solve this by BNB, the branch and bound algorithm. So, we know that the lower bound can be found out by the assignment problem solution. Is it all right? So, how this assignment problem is works out, let us see. So, is the first, if you solve the assignment problem, we take the original problem, we find the row wise minimums and then find out certain number of zeros, right. So, the see 18 is minimum, so we deduct 18, so we get certain number of zeros, is it all right. And then we see the column wise minimum. So, when we take those column wise minimums, 8 is minimum here, 0, 0, 0, 0. So, these 8 become 0 and then we get so many zeros, right. So, obviously, there are m on the the long diagonal. So, we have made row wise and column wise reductions. Now, let us see that how do we make assignments, right. So, how do we make assignments? First we make here A to C, because this is an unique 0, right. There is, this is also an unique 0. So, we make assignments, right. This is also another one. So, we make assignments. Moment you do that, these two assignments are not possible, these two zeros are gone, because we have made assignment here, right. Now, now what happens that this becomes unique then, right. So, we make assignment here, this is also unique, right. So, we make this. So, this 0 is gone. So, obviously, now this has to be assigned. So, that is how we make all the assignments, then that 0 will be not used also, right. So, that is how all the assignments are made. But what is the solution that we have got? We have got A to C, B to A, C to D, D to B, E to F and F to E. And if you look at all these figures, then we get the T C star equal to 80. So, what is the TS problem solution? A to C, D to A to C, C to D, D to B, B to A. So, we have a subtour here, we have another subtour here. So, it is not a complete tour. So, we need to branch further. So, how do you branch? Now, this time you should tell which is the smallest subtour. Just look at it carefully, it should be E to F and F to E, that is the smallest subtour. So, we should therefore, in two branches block E to F and another branch we block F to E, right. So, let us see how it is done. So, we take E F bar and F E bar, and so first of all E to F we put M and F to E we put M, and then we get two sub problems P 1 and P 2, right. So, these two has to be solved. So, this is how when these two solved. So, assignment solutions we are not showing anymore, you have to work them out, please work them out to really find the as the method shown earlier. So, you see the solution comes as such that for P 1 problem we get 84 as the T C star and P 2 we get 87. But while 87 is feasible, the 84, the P 1 is not. So, you see which one is the lowest of the bounds? It is 84, not 87. So, out of those two, 84 is the lowest. So, 87 is feasible, but 84 is infeasible. So, since it is infeasible, we have to branch it once again, right. So, again since the solution is A to C to A, B to F to E to D to B. So, obviously, this A to C to A we should then branch A to C bar and C to A bar, is it all right. So, these two we should do in our next iteration to get P 3 and P 4. So, that is what has been done here, and after solving we find P 3 equal to 93 feasible and P 4 is equal to 90 feasible. So, these solutions are compared. look here, if I see all the n nodes, so these are my n nodes, right. These are my n nodes and they are all feasible, that means all have fathomed. Since all have fathomed, the question here is they are all feasible, the bounds are 87, 93 and 90 and 87 is the lowest, right. So, that should be our optimal tour and AC that is feasible also. So, that is going to be our optimal travelling salesman solution and that DC star will be 87, right. So, this is how we solve travelling salesman problem by branch and bound algorithm, right. With that we stop here. Thank you very much.